All right, so we're going to, again, learn some more new rules for finding derivatives without having to use our specific limit definition, although I will use the limit definition to help me prove some of these rules. Derivative of a constant is 0. Did we already do this one? I think we did. But there's the proof. Remember, a constant is just a horizontal line. So a horizontal line will always have a slope of 0. We did already prove this one, so I'm going to move on. Sorry, I threw it in both sets of notes. We did it in 2.5 because we did this and we did x as well. So I'm going to skip these. Okay, the first one is called the constant multiple rule. So here's what you have to remember. C is a constant, and your function f is a differentiable function. Then the derivative of a constant times your function is the same as equal to the constant times the derivative of your function. And so here is why. I'm letting g of x equal c times f of x. Then g prime will equal the limit as h goes to 0 of g of x plus h minus g of x over h, which is the limit as h approaches 0 of c times f of x plus h minus c times f of x over h. Well, c is a constant. It's in both terms in the numerator, so I can factor it out, meaning this equals the limit as h approaches 0 of c times f of x plus h minus f of x over h. So I just factored the c out of the numerator. And in fact, we had a property of limits that said if you're taking a limit of a constant times a function, you can actually take the limit out, take the constant multiple out of the limit and put it in front, multiply it after. So that's just referencing a property of limits that we had a while back. So now I have c times the limit of f of x plus h minus f of x over h, which, notice what this is. That's a special limit. In the chat, what does that limit show us? What is that limit finding? Yeah, what prime? The derivative of what function, though, now? Yeah. So what we have then is c times f prime of x. And we've then proven our conclusion, right? That the derivative of c times f of x is just c times f prime of x. All right, give me a green check when it's safe to move on. All right, so that makes it really helpful to do problems like this. Okay, it kind of expands the functions that we can easily take the derivative of now. Before this rule, all we had was the power rule, so we needed a function that was x to a power if we wanted to use the power rule, but now we've expanded it to functions that are constants times x to a power. So using the rule kind of strictly, what I have is that this is equal to, I can pull out the constant multiple, 3 times the derivative of x to the 4th. All right, what's the derivative of x to the 4th? There we go, 4x cubed. So I have 3 times 4x cubed, which simplifies to 12x cubed. Now this, again, let's use our kind of intuitive geometry knowledge. The function y equals negative x is just a line. What's the slope of negative x? What's the slope of y equals negative x? Right, -1. So we would expect this derivative to come out to -1. But let's see if our new rules kind of bear that out for us. So really this is -1 times x to the first power. So my constant multiple rule says I can rewrite it as -1 times the derivative of what I really have is x to the first power, which if I follow my power rule would be -1 times 1x to the 0 power. Well, what's x to the 0? X to the 0 is just 1, right? So I have -1 times 1, which is -1, which is, again, what our sort of geometric intuition told us it should be. All right. Give me a green check if that example makes sense and you're ready to move on. All right. Write down just what's in the blue box. You don't have to write the proof out. I'm just going to walk you through it real quick. But do write down what's in the blue box. And then give me a green check, and then you can just put your pencil down and just follow me through the proof. So basically, this is a really powerful one because it's going to open up being able to differentiate any polynomial function. No problem, right? So what it says is if you're trying to take the derivative of the sum of two functions, then you're allowed to differentiate each term separately. Basically, it says we're allowed to do what's called term-by-term differentiation, okay? So the way we prove that is we let capital X, capital F, be the sum of f plus g. And then we're just applying our limit definition of derivative, right? Nothing new there. So f prime would be the limit as h approaches 0 of capital F of x plus h minus f of x over h. But now we're going to replace capital F with the right-hand side equivalence. Right? So f of x plus h becomes this, which is lowercase f of x plus h plus g of x plus h. And then we get minus the sum of just f plus g. And then we're just going to rearrange some terms. I'm going to move this negative f of x to be over by f of x plus h. And then this is going to be a negative g of x. It's going to get moved over by g of x plus h. And then I'm going to separate, which basically they're just using this property. If I have a plus b over n, that is a over n plus b over n, right? It's just the property of common denominators. And so now I'm looking at these two separate rational expressions. We'll notice that if we apply the limit to each one of those separately, each of those is just the definition of f prime and the definition of g prime separately, and this comes out to f prime plus g prime. So this is going to be really useful for us because now if we have a polynomial and we're trying to differentiate it, we can actually just take the derivative of each term individually. So go ahead and write this down. The same is true and the proof holds if it's f minus g as well, okay? I'm not going to redo it. You just have to rearrange things a little bit differently. But if you have the difference of two terms, then you can differentiate those two terms separately as well. I'll leave it here for a second. So now we have this huge polynomial that's the sum and difference of a bunch of different terms. But we now know that we can just differentiate those terms all separately, right? So this just becomes 8x to the 7th plus, what's the derivative of 12x to the 5th going to be? Good. So now you can do this kind of quickly. The constant multiple rule just says, well, the 12 is just going to get multiplied by whatever the derivative of x to the 5th is. So 12 times 5x to the 4th becomes 60x to the 4th minus 16x cubed plus 30x squared minus 6. What's the derivative of any constant? That's right, 0. So the 5 just becomes a 0 because the derivative of 5 would be 0. And there we have it. That's the derivative of that function. Questions? So I want to find the points on this curve where the tangent line is horizontal. What's the value of a horizontal tangent slope? What's the value of a horizontal slope? 0? And what's the calculus term for slope of a tangent? What's the vocab term for slope of a tangent? What does that mean? Derivative. So essentially, I want to know, where is y prime equal to 0, right? So when I say where, that's a location. Is a location generally an x coordinate or a y coordinate? It's at least an x coordinate. In this case, they say find the points, so we're going to want to list the full coordinate. But location, minimum, you're always finding x coordinate, right? All right, so we want to know where y prime equals 0. Go ahead and find the derivative of that function, y prime. And if you get an answer, put it in the chat for me.
Wait, how do you find a derivative on any point you want?
No, I'm asking for the general derivative of the function. So differentiate this function with respect to x. So it would be 4x cubed, that's the derivative of the first term, minus 12x, that's the derivative of the second term. The derivative of 4 is 0, right? So we want to figure out where this is equal to 0. So we're going to set it equal to 0. We're going to solve for x. Well, anytime you have a function equal to 0 and you're solving for x, if you can factor, that's best. Here I can factor out 4x, and I'm left with x squared minus 3, right? Now I can set the factors separately equal to 0, so 4x equals 0, x squared minus 3 equals 0. And I'll go ahead and solve both. So I get x equals 0, and I get plus or minus root 3. But again, they say find the points, and to me, points indicates I want the full coordinates. These are just x coordinates, right? So if I want the y coordinates of the points, what do?
You plug it into the original equation.
Good, the original function, the original y, right? So for example, I want y of 0, which is 0 to the fourth minus 6 times 0 squared plus 4. So it's 0, 4. So on my original curve, I should have a horizontal tangent at 0, 4. We will check this. What about when I plug in root 3? That one's a little messier. Root 3 to the fourth minus 6 times root 3 squared plus 4. So root 3 to the fourth, I think, is 9. Minus 18 plus 4. Negative 5. And because all the exponents are positive, when we plug in negative root 3, we also get negative 5, right? All right, so we should have 3 coordinates. We should have 0, 4, and plus or minus root 3, negative 5. Let's check this in GeoGebra.
Wait, couldn't you just say just root 3 because all the exponents are positive? Or all the x coordinates are positive?
The x coordinates aren't necessarily, right? We have positive or negative root 3. But the exponents are positive, which was my point here, that even if we plug in negative root 3 and raise it to the fourth, you're going to get the same answer as when you plug in positive root 3.
Okay.
Oh, crap. What? Okay. All right, let's look at this. So we have our original function, which is and we found 3 points that we said there should be a horizontal tangent, which was so sorry, 0, 4, right there. Square root of 3 comma negative 5. Which is down there. And then negative square root of 3 comma negative 5. Now all those points we do have horizontal tangents, right? If I zoom in, you're going to see that line flatten out. We're going to have a horizontal tangent at that point.
Mr. Toller,
Go ahead.
you rather us do this like algebraically rather than graphing it, or is there a specific method?
Yeah, if I asked you to do this on the test, you would do the work that I just showed on the actual slide, right? So I'm just trying to solidify your understanding by showing you the graphical interpretation. If you had time, you could go in, throw the graph in your calculator and just make sure it made sense that those were horizontal tangents. But no, I don't expect you to provide me with multiple justifications. The sort of analytical work that we did on the actual slide, this work is what I would expect. Sorry, I'm sharing the wrong screen. Oh, did I not? Was I just not showing you GeoGebra at all? I apologize. Well, you'll be able to see it on the video that I upload because it was recording. But that's the graph, and there are the points. And I zoomed way in on that point to show you that it flattened out. So those are the 3 points, and you can kind of clearly see they have that. They're going to have horizontal tangents because the more I zoom in, the more you can see it's going to get horizontal. Does that make sense?
Oh, also, so does that mean that on the derivative graph, it's the points at which it intersects the x-axis?
That's absolutely exactly what it means. So let's look at that real quick. If I reshare. Zoom out. Yeah, so at all 3 of those points that you're going to see that that's where the derivative graph will intersect the x-axis. Here you go, I'll just do f prime. Yep, so 1, 2, and 3. All right, let's move on. But this is the work you would show on an exam for a problem like this. All right, let's add some context. So the equation of motion of a particle is s equals 2t cubed minus...
Mr. Fuller,
Yeah,
you're still showing the graph.
damn it. Thank you. The equation of motion is given by s equals 2t cubed minus 5t squared plus 3t minus 4, where s is measured in centimeters and t in seconds. Find the acceleration as a function of time, and what is the acceleration after 2 seconds? So essentially, they're giving us a position versus time graph, where x is time in seconds, and your y is position in centimeters. Let's not worry about what that graph looks like, but what units would the slope have? The slope would be in what units? Rise over run. Centimeters per second, which is a measure of what? Or velocity, more specifically, right? So we established this before. The derivative of position gives us velocity. What does the derivative of velocity give us? Acceleration. Excellent. So we're given position. The first thing we'll do is find velocity. So velocity is the derivative of position. I'll just take the derivative of this function term by term. That's going to give me what? 6t squared minus 10t plus 3, and that's it. And what they want is the acceleration after 2 seconds. So next I'll get to acceleration by taking the derivative of the velocity function that I just found, which will end up being the second derivative of my position function, right? Which is just going to be what? 12t minus 10. So acceleration at time t is given by the function 12t minus 10. And now they just want a specific acceleration at a specific time. That would be acceleration at time 2 equals 12 times 2 minus 10. 24 minus 10 is 14. What are the units of my acceleration? Centimeters per second, which is centimeters per second squared. One more rule today. We got this thing called the product rule. This is a little bit of a mess, but we'll go over it. Go ahead and write this down. What's in the blue box, and then give me a green check and I'll explain how this works. And we'll also give you kind of the prime notation, which is a little less nasty to look at. So there we got the proof. You just have to be able to use it. So let's use it. Here's an example. Here we have the product of two functions. Let's think of the first one as f, the second one as g. So it's going to be f g prime plus g f prime, right? All right, so that's going to give me, I leave f alone. The derivative of that second factor, just using the power and the constant multiple rule, would be 28x to the third, right? Plus, I leave that second one alone. That's just 7x to the fourth times the derivative of the first one would be 18x squared. Boom. Now we do want to simplify if we can at this point. So let's multiply these out. What's 6 times 28? We got 168. This would be x to what power? What do you do with the exponents when you have a product of powers? X to the third times x to the third makes x to the sixth. You add them, right? So yes, 168x to the 6th plus 7 times 18 is 126 times x to what? The 6th again. Oh, these are common, these are like terms. So I can add them. 168 plus 126 is 294. And here, it would be x to the 6th, because they're like terms, so you wouldn't do anything with their exponents. Now, something I wanted to show you, you didn't actually have to use the power rule, or sorry, the product rule here. We did, and it works, but we could have just simplified this first. Multiplied it out. What's 6 times 7? (42x to the 7th). All right, that's still the original function. I just multiplied it out. So now if you just do f prime, you can just use the constant multiple rule and the power rule. I bet you can't guess what 42 times 7 is. (294x to the 6th). And that's something to keep an eye out for, because we're going to learn a couple more rules that'll help you out. But if you can simplify your function before doing calculus with it, that's always going to be easier and faster. The product rule is fine, You can see there's a couple of extra intermediate steps that you have to use. So if you can avoid it by simplifying, that's always good to do. That'll save you time. But there are situations where you can't avoid it, okay? Something like this, where it's much more abstract. I'm not actually giving you the algebra for all the functions. I'm actually just naming them. And then I'm giving you little snippets of information to be able to fill in. So we're given that h of x is x times g of x. Then we're given certain values of g and g prime at 3, and they want us to find h prime at 3, right? So the first thing we're going to do is find h prime of x in general. So it makes sense in this case. We'll think of it's a product there. It's x times g of x. So let's think of the x as my f and the g as, I guess it makes sense to call that g, right? And so what we're going to have is f times g prime. So that's x times g prime of x. Plus g, so g of x, times the derivative of my f function, times f prime. What's the derivative of x? Help me out in the chat. What's the derivative of x? 1. So it's just times 1. Great. So there's my general derivative for h. Now I want to know h prime at 3. So all my x's just get replaced with 3. So I'll have 3 times g prime at 3 plus g of 3. And this is where that extra information that they give us comes in. I know that g prime at 3 is 2. So I have 3 times 2. Plus, I know that g of 3 is 5. So plus 5. So 3 times 2 plus 5 is 11. Therefore, h prime at 3 equals 11.